Good afternoon. So, in the last class we looked at Einstein's derivation of the random walk problem, right? And we saw how he used the basic idea that the particle or each particle in the group, right, is undergoing these random steps at intervals of time tau, and then just by specifying that these random steps are a random process with some distribution, he used a probability balance to ultimately derive the diffusion equation. So, what we want to do in today's class is to look at the Langevin equation, right, or Langevin's derivation, where Langevin said, let me actually just focus on the evolution of an individual particle, and from there, by treating it like some kind of ODE, try to arrive at the mean square displacement evolution with time, right? Exactly in the end what Einstein derived using the probability distribution function. Remember, after we derived it, we solved the diffusion equation for a Dirac delta initial condition, and then we used the PDF to calculate the ensemble average of x square with time and found that it grew linearly, right? So, it's the same thing that Langevin wanted to arrive at, but just by using an equation for the evolution of one individual x, okay. So, but before we do that, I wanted to make some comments on Einstein's derivation, which, because it has certain ingredients that we will encounter in a more formal, more rigorous setting during the course. Okay, so these are, if you like, the key ingredients, right? So, the first thing is he started with this idea that each particle is undergoing this random step, all right, and the key assumption is that each step is independent of anything in its past, right. So, such stochastic processes which do not depend on their past history are called Markov processes. So, the first point is that the okay, so there is, in other words, the distribution phi, right, that I specified for each delta. I could specify it once and for all, regardless of where the particle is, where it has been, etc. Right? It's just, no matter where it is, it does something, or whatever process it's undergoing has forgotten the past. Okay, so that's how you can specify just one PDF for that step delta. So this is of course an assumption, okay, and the assumption works if the physical process that you're looking at is somehow decorrelating in time, which means it's forgetting, right, its past, because of course at the micro scale there is some microstructure which is evolving, if you zoom sufficiently, which is evolving continuously, right. So there's of course some history, right, that's the inherent idea in any ordinary differential equation, right, that it is evolving with some history, etc. And if the idea is you have waited for sufficient time, that's where the tau definition is important, right, where it has forgotten where it is. Okay, so this is the first point, and this was used to simplify the probability balance. Okay, so the second thing he did was a balance of, okay, I'll call it probability balance. You can look back to your notes, right, that is where he wrote down that integral relation. So the probability of finding a particle at some position x at time t plus tau is given by summing up all the probabilities of finding positions at x plus minus delta and taking the appropriate step delta, right. So that is basically some kind of mass balance or probability balance. Okay, in that you can of course always write a probability balance, right, because as long as particles are moving around, you can do some kind of conservation and write a balance. But how complicated the balance is depends on your assumptions. So because we assume that it is Markov and it has forgotten, then we can write the balance very easily, right, because you just have to take the probability and use it to weight the PDF of the step, the probability to take a certain step delta. But if that step delta depended on where the particle had been, you would have to do a multiplication of probabilities, right. You would have to, suppose it depended on its history, you would have to say probability of starting at some point and then going here and then going here and then going there and now taking a step delta. You see, so you would be multiplying probabilities and you would have to specify the probability at each of those sub-steps. Right? So it quickly becomes a very hard problem. So we will look at this in the future classes, looking at stochastic processes in the most general case and then seeing what the assumption of Markov really does to simplify things. But already you can see that it was a very simple one-step balance, and at the heart of that simplicity was this assumption. Okay. So this probability balance, which one can always write in more or less that form for a Markov process, is also called the Chapman-Kolmogorov equation. So in the latter part of the course, when we do it in a general, more careful way, we will introduce it as a Chapman-Kolmogorov balance equation. But it is essentially what Einstein did, in some essential fashion. Okay, so you write down that integral relation, and then the most important thing we did was to go from that somehow to a PDE, right, for the probability. And that involved what? Right, we did a Taylor, some kind of Taylor series expansion, right? Again, this involved assumptions on the tau being small, on delta being small. Now, this is also a standard move, because whenever one has to go from the Chapman-Kolmogorov to some kind of PDE like evolution equation, one has to do something like this Taylor series. And also in more general contexts, such Taylor series treatments are used, and there they are called a Kramers-Moyal expansion. So again, this will be done, more formal way of saying the same thing, but it's the same idea, right? So you can see, as characterizes Einstein's genius, right? He had all these ideas, right, in his seminal work, which people then took and developed and made more rigorous, etc. So now in this Taylor series expansion, other than the fact that we had pointed out last time that you are assuming that delta is small, that even though you have specified some PDF phi of delta which you have not given any information about, right? So it could be that you have quite large probabilities for large deltas, in which case this expansion becomes questionable and so on. So these are things we look at later. Same thing for tau, right? How do you know tau? Of course you are choosing tau, but can you really choose a tau of that kind which satisfies the Markov assumption and is small? Right? So these are questions we'll address. Beyond that, there was an interesting move, conceptual move that is made, So when we did the Taylor series, it's very simple to do algebraically, right? You just apply Taylor series. But conceptually, we made a subtle shift, because what we started with was saying that I'm looking at a process that is discrete in time. That was the whole idea, that I look at time intervals tau, and on those time intervals I can say the movement is random and uncorrelated with the past. But now by doing the Taylor series, remember we introduced a d by dt, which means time became continuous, right, like it is in an ODE. So we started with a discrete, if you like, random stochastic process, which is also a valid way to look at stochastic things. You can say I'm going to live in the discrete world. But then we made this shift via this Taylor series type treatment to a continuous in time stochastic process, which is there because we have a d by dt now, right? It's become continuous in time. And the PDF evolves continuous in time and is in fact the same as the concentration field, right? Which we've always thought of as evolving continuously in time. So there is a shift from a discrete to a continuous stochastic process that is done when one does this, and it's a standard thing that is done often in analyzing such stochastic systems. Now the underlying idea is, of course, so there's a lot of this, if you like, phenomenological modeling that goes on, right, in stochastic processes, because we are of course using stochasticity to, if you encapsulate all the stuff we don't know. So at the small scales, at the microscopic scales, a whole bunch of things are going on. And again, as Einstein said, the idea is if I look at it at large enough time intervals, all of this will just decorrelate the stuff, I'll put it into the randomness. But at the same time, I want to use the mathematical machinery of smooth PDEs, right, in time. So one way to think about this, apart from the way one can justify it mathematically, is to think that, I have some model, I'm going to model this stochastic process smooth in time and look at some quantities, like the PDF which has all the information, right? Or some conditioned PDF, whatever, you can extract it from after you solve this PDF equation, the diffusion equation. And then what you do is compare this to whatever you are observing. And at that level, you will decide whether the model makes sense or not. So in other words, there could be a system which is actually doing discrete jumps, like it's just hopping around. Right? But you decide to represent this by a smooth trajectory. And in the end, if all you're interested in is some large-scale features of how it is moving, you are okay if your smooth trajectory is able to pass through those points where this guy is jumping. So it depends on what you're trying to model. So again, at this level is just to since we have already done the derivation, for you to look back and recognize these steps. What was the fourth thing I wanted to say? Yes. So finally, we ended up with a diffusion-like equation. So it could be advection diffusion also, right? If I had a bias in my stepping, right? For the probability, right? And this kind of diffusion equation will arise not just in Brownian motion. So in this particular example, we're actually looking at a particle that's moving around, right? So it's natural, I mean, and it gives you actually what we think of as a diffusion equation. However, you could have this kind of probabilistic stepping around in any landscape. It doesn't have to be physical space. It can be a stock market price, okay, where it is moving around in this space of value, right? Or it can be anything, any other process, higher dimensional process. It can be a chemical reaction, right, where the concentration is fluctuating in concentration space. So in all those cases, similar derivations can be done in the appropriate space, and you will get also something that looks like a diffusion equation, except instead of having d square by dx square where x is space, x is going to be some other state variable now, right? It can be value, concentration, or something else. But in general, so all those equations have the same form, right? They are all called Fokker-Planck equations, or you can also just call it a diffusion equation. Okay, so that's what we will see again in this course and in a more general way, right? So in this case, we've done it specifically for Brownian motion, but in the coming classes, we look at a general stochastic process, and we'll see how we can formalize these steps and arrive at a general diffusion equation. Okay. Any questions about these points? So if you go back to your notes, at those appropriate steps, you could just mark these things down. Okay, then at the end of the last lecture, I had also pointed out, which I will just remind you of, that what we had derived is to take this Brownian motion with some kind of step, right? We didn't specify anything particular about phi. And all you need is the first moment, which will give you the advection, right? And the second moment of that distribution, probability distribution of the steps gives you the diffusion coefficient. Okay. But one should not think that this means that any kind of Brownian motion, okay, or if I may generalize it, if I see a particle that seems to be hopping around in some stochastic way, doesn't mean it has to be following a diffusion equation. Specifically, based on what we derived, it doesn't mean that the mean square displacement in the appropriate space, so if you take a bunch of particles at some point and they spread out, right, because of random movement, it doesn't mean that that spreading out will grow as x square growing like t, or as the radius of the ball growing like root t. That is purely, that's the case, that is, it happens in the case of pure diffusion, which will follow from this derivation. Okay. However, as I mentioned last time, right, you can have super diffusion when things spread out faster, and you can have subdiffusion where they spread out slower than root t. Like, for example, t to the 3 by 4 is close, right, is higher than t to the half, that is super, and some exponent less than half will be sub. And super diffusion, I pointed out, can happen when when there's a high probability of taking large steps, right? That will mean that I can no longer neglect the higher terms in the Taylor series because the higher order moments are not finite, right? They're blowing up. Okay. That just means that for example, the fourth order moment, if phi doesn't decay faster than x to the minus 4, that integral will not converge. And then similarly on the other side, right, when you say subdiffusion, one way to think about this is if I was to flip it around and say, let me look at the distribution of times it takes my particle to take steps of some size. Okay, what we have done is assume that I can define a fixed time interval tau, and then I get a distribution of steps delta it takes in fixed times. I can of course flip this around, right? I can say, let me observe the particle, and whenever so it's doing something, and then whenever it reaches delta x from the starting point, I mark the time. Right? I can keep doing this exercise. I'll now get a distribution of waiting times, right? This is the time it takes to cover some distance because of whatever process it's doing. Now, if that waiting time distribution has a mean, okay, that's one way to choose a tau, for example. But you could have situations where there is no mean, right? Because the mean time would be integral t PDF of having a certain t, right? And if that PDF doesn't decrease faster than t to the minus 1, this integral will not exist. Okay, so it means that the probability of large times is high enough that you don't get a converged mean. Okay, so there is always some substantial chance to be waiting for arbitrarily long. And this can happen if you have a particle physically, if there's a particle diffusing, for example, in a porous media, because then it's not free, right? It can go into some trap and it can get stuck there. Or it can happen if you're studying the configuration of some molecule. So it is diffusion now in the configuration space, and for whatever reason, because it is in some network, right, then it gets stuck in some particular configuration and it almost doesn't change. So these are subdiffusive processes. So again, there our derivation will break, right, because we will not be able to define this tau in a meaningful way. Okay, so there are a lot of hidden assumptions which I've tried to point out. But okay, having said all of that, the typical case of Brownian motion, you get the diffusion equation. Again, we'll come back to these things more carefully. Okay, any questions? Fine. Okay, if not, we'll leave Einstein. And let's go to Langevin, okay, in 1906. So Einstein's paper appeared in 1905, right? That's around the time he did several great things. So 1905, his paper appeared. 1906, Smoluchowski's paper appeared, which was more or less along similar lines as Einstein, looking at the PDF and so on. And then a different approach was taken by Langevin, also in 1906. Okay, so all these people did these things sort of independently, were thinking about similar problems. Okay, and Langevin says that his technique arrives to the mean square displacement in a way that's infinitely more simple. So let us see it. But as you'll see, usually this simplicity, it will be simple in terms of the derivation, but there's a lot of subtlety inside. Okay, so what he said is, I don't care about all this probability distribution stuff, right? I just want to look at one particle, and I should treat it the way, like, you know, Newton treated a moving object. Right? I should be able to write Newton's laws for this particle. Okay, if it's fluctuating, I'll put some fluctuating force, and I should just be able to treat it like an ODE and figure out how it is moving. Right? Why should I have to solve a partial differential equation if I want to know how a single particle is moving? So that's one way to think about it. And therefore, he gave birth to the alternative way of looking at stochastic processes. Rather than through the probability distribution functions, which are smooth functions and give rise to PDEs, you think about individual trajectories, okay, and that will naturally give rise to what are stochastic differential equations. Okay, so he said, let me look at the particle x. Okay, it's here, it's doing this stuff. Okay, and the position of the particle is x, and it's evolving with time. And so if I have x evolving with time, then I can of course define b is dx dt. Now immediately you may get worried that if it's doing this random erratic motion, how do I know that its derivative exists? Right? Maybe the velocity is infinite because it's changing very rapidly. So don't worry about it for now, right? That is the idea. So he just proceeds and then we see how far he can go. Because if you think about it, there were similar assumptions also in, right, Einstein's work. Right? So this is, remember, the beginning of the field, and this sort of attitude of just forging ahead is instructive. Okay, so let's do that. So let's now apply Newton's laws. So you say that I have this particle, right? It's sitting in a bath, remember, and let's say it has mass m, then it has position x as a function of time and a velocity, okay, which I assume I can define. And similarly for acceleration and so on. And now, whereas Einstein kept in his mind clearly that, okay, this guy is doing some random motion at intervals of time tau, so he did away with any thoughts of applying Newton's laws and so on. Here we do the opposite. We say, okay, let me treat it as if it is just a particle sitting in a continuum fluid. Okay. But I know it is fluctuating, so I will put in some fluctuating force. But before I get to the fluctuations, I know how it would move in a fluid, right? So you would write mass into acceleration, right, is equal to the sum of forces, right, that act on the fluid. So if the particle is moving with some velocity v through a continuum fluid, what force will act on it? Forgetting the fluctuating part for now, it's just in a fluid, it's a big particle in a fluid. okay, like a ball, and it's moving through the fluid, then what force will act on it? Yeah, so do you have, okay, so let's say that the particle is small, it's in the Stokes regime, then is there some simple formula you can apply which directly gives you the net force on the particle? Anyone? Right, so you'll have a drag force, right, on the particle. What is the law? So you'll have the Stokes law, right, for the drag on a sphere. Okay, so you assume it's a spherical particle. If there's a particle moving through the fluid, right, there's of course some force that's pulling it. It could be gravity or whatever. But there is also a retarding force which tries to make it relax to the background velocity. That's the Stokes drag. Okay. So this is a drag coefficient. We'll put in the formula. It's 6 pi viscosity radius, okay, and linear proportional to V. So we'll say that it can be described by a drag force which is 6 pi mu r. Okay, mu is the fluid viscosity. And then V is the velocity, right, because the background fluid is static. Okay, if the background fluid was moving, then you would have V minus U of the background fluid. But here it is static. So if it is just by this self, it will tell me that even if I start with some motion, it will come to rest. Right? Clearly. But now something is keeping it in motion, right, because the particle is doing this. So this is where, of course, he has to use the fact that the net force is coming because of the molecular character of the background fluid, right? So that there are all these bombardments and it's giving some net force, and that net force is random because it's a sum of all these different bombardments which themselves are happening randomly, right? So he adds a stochastic force, which is some function of time and it's fluctuating stochastically. Now at this point he says nothing more about, or one need not say anything more about this force, okay, even though it's a very mysterious thing, right? But we'll see at some point he will have to say something, and only that is what one needs at this level, okay? But of course that raises many questions, we'll address that. Okay, but at this point what is sort of maybe discomforting but also ingenious, right, is the combination of terms, right? So here up to this point, right, if you forget about this looks like a continuum description, right? It's what I would apply to any size, massive size sphere where I don't know that the world is atomistic, right? I just say there's a particle, it's sitting in a fluid, and I can derive the Stokes drag exactly, right, from Stokes equations. But then because obviously the phenomena it reveals the microscopic nature of the background fluid, right? That is why it is moving, otherwise it would just stay there. So he just chucks in by brute force this stochastic force to account for the fact that actually there are fluctuations. Okay, so it's a kind of mix of the continuum perspective and the molecular perspective, right, which is not really there here. Okay. Here I don't have to assume any such thing. I just start with the fact that I have some object, some particle, it's doing these random jumps, and I can derive a diffusion equation. Then if you ask me what is the diffusion D, right, then I have to use some statistical mechanics and say D is coming because there are molecular fluctuations which have to do with thermal noise, and in the end Einstein does that in his paper and he derives his Einstein diffusivity. He relates the kinetic energy of the molecular motion to kT, Boltzmann's constant temperature. But that comes later, right? To make the initial thing, the description of the mechanics is not required. You just say that it's doing these jumps. Whereas here you are immediately confronted with the physics of the process because he is trying to follow an individual trajectory, right, in the classic way. Okay, so we have not said anything about this force, what is its magnitude, right? What do we mean by saying it is stochastic yet? Okay, so this is fine, we assume that we can do this. Now what we really want is the position x, so we move to x. Okay. And now what he wants to do ultimately is get the evolution of the mean square displacement, so x square, okay, because x of course you know is its average of x is going to stay 0 because you're going forward, backward equally. So to get the evolution of x square, the natural thing to do is to multiply with x throughout. Okay. So that's what he does. Or rather, let me say, okay, so I'll get different terms. The first term will be m, and then I have the other term. Right, so these are the three terms, if you like. So this is fine, I'll leave it as it is. And ultimately what I want to do is to take the average, okay, because I want to get the evolution of the average x square. So I would like to bring this inside, right? Similarly, I'd like to bring this inside. Okay, so can you do that? Use chain rule and see if you can bring it in the form of d dt of x square, and if there is a velocity, you can leave it like a velocity also. Okay, sorry, before you do that, the other piece of information that Langevin knows he has to use at some point, because he has not specified anything about the force. Right? So obviously the amount the particle moves is going to depend on what is here. Right? If this is 0, the particle will just become stationary. Right? So it depends on the amplitude of this, but he doesn't know how to specify this. What he knows is what Einstein also uses to get the value of the diffusivity, okay, which is that in a thermal bath, if you just put a particle, there's no external force, you just leave it, right? Then the kinetic energy of the particle will equilibrate with the bath such that half mv square of the particle becomes kT. Right, so this is the temperature. Half kT, sorry. Because this is a result from statistical mechanics and equipartition. For now, we will just accept it. Okay, so if you do this before this work by Einstein and Langevin, we already had kinetic gas theory and the basic ideas of statistical mechanics. So from there, we know that if each of the molecules doing the stuff will have some kinetic energy, okay, at equilibrium, because they're all bouncing around. And similarly, this big particle, foreign object you put, will also have its kinetic energy. And those will be in equilibrium, right? Because we are looking at a bath in equilibrium. Even though the individual things are moving around, there is thermodynamic equilibrium. And at that state, the kinetic energy of the particle will be half kT. Okay, so this is something we know externally. So we would like to use that here. So when you do this manipulation, try to get it as d dt of x square. And if you can get it v or v square, keep it that way. So just try that out. Did someone have a question? Okay, then you can just try it out for a bit. Okay, so you can take a look and see if you're approximating the result. Is that okay? Right, so I took one dt outside the whole thing to get this, and then I accounted for the factor I would get from the chain rule, and then I took the x inside. So basically I got acceleration of the mean square of x square, and I brought in the kinetic energy. So this now minus mv square I can replace by minus kt. Okay, so now let's put the pieces together. So there would be mv square here, which I will replace by kt. Then there is a minus drag coefficient by 2 . Is that okay? Yeah, so the minus mv I took the other side and it became plus mv, which is kt, and then I have minus cd d by dt of x square with the 2 factor and this. Okay, so now I brought it in the form where I have an evolution equation for x square. Okay, and what I want is the root, is the mean, right, of the square of the displacement. So I'll take the ensemble average now. Okay, so I'm going to use angular brackets to signify the ensemble average, and what that means is I do an evolution of one particle that will follow this equation. I can now put another particle and do thousands or millions of these, and then average out their motion at every instant of time, right? So let's say after 10 time steps, or at t equal to some value, let's say 10. So this guy moves this way, this moves this way, this moves this way. So at 10 I can see where all the particles are, I can average over them and I'll get a mean position, right? The mean of x will be 0, but the mean of x square will not be 0, it should hopefully grow in time if what we are doing makes sense. Okay. You can see that the mean of x would be 0 if you look at the original equation also, because the mean of zeta I will say is 0 because it's a stochastic random force. So now let's apply the ensemble average here. So when I put the angular brackets here, I can of course take out m outside, and I can take the ddt also outside, right? Because remember, the ensemble average is just summing up and dividing by n, right? It's a linear operation. So I can of course take the derivative outside. Okay, if you're confused, you imagine you write this equation for I, and then you have I 1, 2, 3, 4, 5, 6 and so on, and now you're just adding them. So I can of course take the derivative out of this operation. So I can bring this in here. The kt will stay as it is, it's not a fluctuating quantity. Similarly, the dt will come in here, and so ensemble average will come in, and this will stay here. Is that fine? So I take an ensemble average, and now is the time I say something crucial about the zeta. Okay. I'm going to say that these things are uncorrelated. So when I take the ensemble average, right? So taking the mean of the product of two quantities, both of them if I treat as random variables, if they are independent of each other, then I can multiply them, right, separately. So this will be the same as, right, if they are uncorrelated. If they are correlated, then I'll have some corrections. But this the product happens only when they are uncorrelated, and then I know immediately that this guy is 0. Well, that's what I'm specifying, that the mean of the stochastic force is 0. It has no mean direction. So I say uncorrelated these are the two statements that Langevin makes about the force in the end. Right? So I don't specify what's the magnitude of the force. Right? In the end, if I have to specify it, it would have to be in terms of some external information anyway, like the kinetic energy that that force should ultimately impart on average. But that I already used directly by replacing mv square by kt. So I've implicitly said that zeta has an amplitude such that the consequent mean velocity will give me kt. Okay. So maybe I should be careful here. Okay, so I had I should be careful, not maybe. I had mv square. I should put the ensemble average on mv square, and then this is of course kt. So I should have been more careful here. Right? So of course, this instantaneous kinetic energy is fluctuating. It's not a constant. Right? It's only the ensemble average that is the constant. So the average over all the kinetic energies is kt. So I cannot replace it there. Instead, when I write the equation and take the average, then the average kinetic energy is kt. I mean half kt. The v square is kt. Okay. And this average goes to 0 because I say that the stochastic force has 0 average and is uncorrelated. So by uncorrelated, specifically it's uncorrelated to where the particle is. Okay. So that means no matter where the particle is, the kind of noise it feels which will make it take some random motion, that is uncorrelated with where the particle is and what its history has been and etc. So if you like, at any point in time this particle gets a hit. Okay. This hit is random. It has nothing to do with the past hits the particle has experienced. That's more specifically what I'm saying. Right? If there was some connection, right, even if the hits were correlated to themselves, right, then all those past hits are sitting inside x, right? Because x is a function of all the past hits. And if all the past hits are correlated to the next hit, these two will be correlated. Or if the hit I get depends on where I am in space for some reason, then also they will be correlated. Okay, so this statement means there is no connection at all between the hit I'm going to experience the next instant from all the hits I got before, and this hit has nothing to do with where I am. So it's actually the same thing that Einstein assumed, right? But in terms of being able to say that delta is a Markov step, right? And that he has a PDF of delta which has nothing to do with x, which has nothing to do with time. Okay, so they both make the same assumptions, but where those assumptions come in is quite different, right? So there, right at the beginning, I recognize this Markov thing, I do the probability balance, and very explicitly I have to make this point that there are random steps, they are uncorrelated, etc. right at the beginning, otherwise I cannot progress. Here, you get all the way till this point, right, and then this is when you realize, oh, you know, if I want to make progress to simple Brownian motion, it can only happen if the stochastic hits I'm experiencing are decorrelated. And of course, I've said nothing about time here, right? So it's instantaneously uncorrelated. Right? No matter how frequently I look at the hits, they are always uncorrelated. Okay, so this is the connection now between this and what Einstein did at the physics level. We are both saying the same thing in terms of the actual force, right? What they mean by stochastic force is that that force is uncorrelated with the past and where this particle is now. All right, so once I do this, I now have a classic ODE. I have gotten rid of the noise. Okay. Right, so now this is a smooth quantity. This is the ensemble average, right? It's a nice function of time. It's no longer, it's not stochastic. Okay, I took the CD to the other side. Now, this is a nice differential equation. I can solve it. It's a linear equation. But to simplify things, and which is also the physically important case, I'm usually interested in a particle which is quite small. That's only when we see Brownian motion. The more massive particles don't show this kind of behavior. So in that usual case, this m by CD is sufficiently small that I can drop this term. If I want to do it properly, you can scale the equation appropriately, but essentially in the limit where this thing is small, you have a tiny particle, right? And specifically, remember, m will go like r cube and CD goes like r, right? So m by CD goes like r square, right? Given some density of the particle. So for small particles, this term will become small, sufficiently small. So typically I can drop this, right? Right, then this equation will simplify and I will immediately get right. So once again you see that the mean square displacement grows in time linearly. Right? This is the same thing we derived from the diffusion equation. And this stuff, right? Right. Is the diffusion coefficient. Okay, so that's just to identify it with the way Einstein did it. So if you write it as 2 times kT by CdT and you identify kT by CD to be the diffusion coefficient, that's the Einstein diffusivity, and then you will get that x square goes like 2 capital D into T. That's exactly what we derived if you look at your previous class notes, right, from the diffusion equation. So of course a factor of 2 is a convention. Right, or x will go, if I take the root mean square displacement, it will go like root 2 dt. Is that okay? Okay, so no questions on the algebra. Fine. So that was trivial, right? But the deeper thing should be causing you unease, okay, because it seems like a magic trick, right? That I started with some equation which I wrote down with some force introducing continuum and molecular things simultaneously, and then just so by using the right relation at the right time you get the result you need, right? So it has that flavor. That's why it's a work of genius, right? But of course you want to know more, right? That what is the magnitude of zeta? That how can I find this zeta even in terms of fine kinetic energy, but there should be some way for me to find it, right? And then I might want to be able to predict other properties about the trajectory x, right? This is one useful thing, but what about other moments, right? Or can I reproduce individual trajectories? And most importantly, from a mathematical perspective, is this x, what kind of function is x, right? So we expect it to be continuous because when I solve, so let's say I can write dx by dt equal to something, x will be equal to time integral of that something, right? So if x is defined as an integral, then definitely it is continuous, right? If that integral makes sense, that's also a question. But since you started with an ODE for x, dx by dt equal to the right hand side, then x is integral of the right hand side. If that integral has any meaning, if it can be defined, then x is continuous. But is x differentiable? Right? We would expect no, because dx by dt has that zeta sitting on the right hand side. And that zeta I just said is like some uncorrelated thing. It doesn't correlate with what it was in the previous time. So then how can it be differentiable or continuous. So x, you don't expect zeta to be continuous, zeta should be jumping. So this suggests that dx by dt cannot be defined, and yet I just did this calculation based on that. Okay, so you see that it looks like there are some contradictions, right, or doesn't make sense, and yet I get the right answer. So something is right, but of course it has to be put on a firm mathematical footing. So these sorts of things were done, of course, at the early part of the 1900s, where people were just doing and thinking about these things for the first time, and it took several decades to formalize things and both in a mathematical and physical way understand exactly what we are doing. So we'll be doing this in the next few classes. Okay, we are going to, again, always before your mind, I want you to keep these two ways of looking at a stochastic process, right? So you see one particle doing something, you should be able to imagine, okay, I can describe this by thinking about the probability distribution function of many such particles, right? They will have some probability distribution, and how will that evolve? So that will be a continuous PD, because the probability distribution is a continuous function. So the moment you introduce a PD, the PDF, the probability distribution function, you're working in function space, the mathematics is nice. Only question is, how do I derive an equation for that probability distribution? So then we'll have to look at a rigorous equivalent of what Einstein did. On the other hand, you say, I can also think about trajectories, right? I don't want to think about the PDF, I want to think about maybe thousands of trajectories over which I can do statistics, but I want to think of trajectories, okay? And then you have to do something like what Langevin did, but of course you need to have a mathematically rigorous way of doing it. You need to understand what is the position x. If it is not differentiable, then how can I think about this evolution equation and so on. And both these things are useful, okay, because of course the PDF, you directly get information of the whole distribution. But maybe sometimes you want to know information about trajectories, and that information you cannot recover from the PDF, right? Because imagine I have the PDF, I start with some Gaussian PDF of the particles, and then after some time it spreads, right, because the particles are spreading, so it will spread out. Right? That's like saying the concentration field has spread out. But now if I want to know what an individual particle did, or some properties of these trajectories, I cannot get it from the PDF, right? Because the PDF is not telling me which specific particle went where, it's just showing me what the whole distribution has done. So I have lost information. So when you go to that PDF, because it's becoming simple, you have averaged out in some sense, you have lost that information. That's why we saw also in Einstein's derivation, remember you can have many microscopic motions that give you the same diffusion equation, right? Any process undergoing random steps which has the same mean and same variance will give you the same diffusion equation, even though now the details of that distribution of delta can be very different. And those different things will affect the trajectories, but not the distribution of what all the trajectories do. All right, so the nice thing though is we have now seen both things right at the beginning, right? And we have seen them connecting together, right? They both describe the same phenomena, give you the same result, okay? But we don't have a rigorous way of connecting the two and of systematically start going from one to the other, right? So for example, with this approach, I cannot directly derive the diffusion equation from here right now, right? I have to take two different views of the problem and arrive at the same answer. But what I would like to do is take one description and rigorously get the other one. Okay, so that's what answering the first part of this course is going to be. Okay, so now in the rest of this class, I want to talk about some computational aspect which will give us a feel for Brownian motion, and which is in fact the subject of the first assignment. Okay. So in the first assignment, what you will be asked to do is to solve this equation. Okay, so where I say, no, not exactly this, yeah, I go back to Langevin's equation, and right in the beginning I say I am neglecting inertia. So I say m by cd is small, then I will just get minus cd dx dt plus zeta equal to 0. Okay. So I will have an equation of the following form. Right, so this is the material for assignment 1. So let's say I have this equation, which will follow from Newton's law when you take the limit of the dissipative limit, right? So you neglect inertia because m by cd is. Then, and I have, you scale things appropriately so that there is no constant factor. Or if you want, you can put some amplitude there, it doesn't matter. the main point is you have an equation like dx by dt is equal to zeta. This zeta is this fluctuating quantity. And to be specific now in assignment 1, we'll say, okay, zeta is a random number which is drawn whenever you need it. Okay. So let me now be more specific. And that's certainly that's an assumption that would be okay for Langevin. So I'll say zeta is a, to be specific, Gaussian random number, but you can use uniform or whatever. So what I want to do is computationally simulate a random walk, okay, which is consistent with the kind of motion Langevin was thinking about. So I would say dx by dt is equal to some stochastic force and in 1D. And in 1D, one way to realize this is to say that zeta, which is pushing me, is drawn from a random distribution. And every time I need to apply the zeta to the particle, I take a new random number. Right? So this exercise of drawing from the distribution will of course give me a sequence of zetas. So I'll have zeta at t1, t2, t3. This is a vector of zetas, a sequence of zetas. Each of the zetas are uncorrelated with each other because I've taken them randomly. Right? And therefore they will be uncorrelated with x. Right? So whatever x I am, I'm anyway taking the zeta from the Gaussian distribution. It has nothing to do with my x. Right? So this will certainly work. Okay, so this sort of prescription is something that would be fine for Langevin, and I should get this result. Okay, of course, if I tune the amplitude of zeta. So the amplitude of zeta will just affect what d is. Right? It will not, what I am looking for is, will x square grow linearly in time? Okay, then if I choose the amplitude correctly, I can get whatever diffusion coefficient I want. So in other words, this amplitude, if I put a there, will be related to d in some way. But without worrying about that, the very first question is, suppose I do a simulation like this. Right? I try to solve this ordinary differential equation where zeta is drawn from this Gaussian or uniform random number distribution. Will a collection of particles x starting at the origin spread out in this manner, right? Where the mean square displacement growing like t? That should happen because that's what I've assumed and done the derivation. So the point is now about how will we solve this, right? So I cannot solve this ODE, how will I solve the ODE numerically? I have to do it numerically, of course, this is a random number. So one simple thing to do is to try Euler's method. So again, we are sort of again forging ahead without worrying too much because the idea is to develop some intuition. Then we will revisit this rigorously. So let's say I look at this thing and treat it like an ODE and say, let me use Euler's method. Immediately that gives me a very precise way of generating the time sequence of zeta because I can say I will divide time into intervals of delta t. Right? So then I will need zeta only at intervals of delta t, and that means I can draw zetas from the distribution at every delta t. So then immediately I'll get something like delta x is equal to zeta delta t is my Euler stepping equation. Okay, so I start with some x and then I find the step as the random number into delta t. Okay, this would also satisfy Einstein's starting assumptions, right? Because he made assumptions on delta x. He said that should have some finite variance, right? Zero mean, and should be uncorrelated. And that's exactly what we'll get from here, right? Because the mean of this is the mean of this. The mean of zeta will be 0. Right? It's a Gaussian 0 mean. And if I look at the variance of this, it's the variance of zeta, which depends on whatever variance I choose for that, right? Something finite. You can say 1 for now. So this kind of prescription will work for Langevin and for Einstein. So both cases I should get diffusive motion. Okay, so far so good. So now I want to check what will happen to x square if I actually do this kind of calculation. Right? So x is nothing but summation I goes from 1 to n, right? Delta xi. This is, if you like, delta xi, zeta I. The zeta i's are drawn from that. But this also means now that, let's see what happens if I take x square. It will be a double sum, right, over I over j. You agree? I have to keep different i's and j's because they are two separate x. And now if I take the ensemble, right, I want to know this thing. How will it evolve in time? So I have to apply the variance across both of this. But now immediately you will see that these two are uncorrelated, right? Because these two are nothing but those zeta i's, delta t square, and zeta I, zeta j is uncorrelated. No? They are two different random numbers. So immediately I will get this to be the summation okay, so if you want, what I would have to do is, when I take the product, I will get delta xi when I and j are equal, right, that will give me this, and when I and j are unequal, and when they are unequal, they will become 0, right. So it's only when they are equal that it will survive, right? So I get this. But this is the standard thing, you know, right, that if you have uncorrelated random numbers, the variance of the sum of these things is the sum of the variances. Right? This is a basic probability thing. So that's what we have done here, that's all, right. So in other words, the mean square displacement is nothing but the sum of the variances of my steps, right, and all of that is the same, right. The variance of this is the same, right. So I'm just going to get n, right, the n will come from summing up all these variances, each variance is equal. So it's the variance of my zeta, right, and then delta t square. You agree? The variance of this is just variance of this delta t square. But now you see, now this n is the number of time steps, right? So I'm going to have n, and what is this? Delta t is capital T by n, right? If t is the total time. That should be shocking. There's a problem with this physically. So what is the problem? So what we've done is, this is a standard random walk, right, that the variance, mean square variance, is the sum of the variance of my steps. So in other words, the mean square displacement should grow like n into my variance, which is fine. The problem is the variance now depends on the delta t, okay. So in the end, if I follow this Euler discretization of some Langevin type equation, I am going to get a mean square displacement that depends on n. Okay, so I am trying to do a simulation for some time capital T, and what this is telling me is the resolution at which I do this simulation will change the answer. Okay, which doesn't make sense. So when you think of a ODE, right, and you solve an ODE with some discretization method, the whole meaning of doing a numerical simulation is if I divide things into small steps delta t, if I make delta t sufficiently small, I should converge, right? Only then if I have any hope of it being accurate. It may still not be accurate, but at least it should converge. But here you think, of course it's not, it's telling you it's not going to converge, right? The more number of steps I take, the smaller the delta t, the less will be my variance. You agree with that? I mean, agree with what we have derived, right? Then we have to figure out what happened. Okay, so there is a problem. So what this means is, without knowing why fundamentally, right, just from this kind of empirical way, we realize that if I have to make any sense of this, like as a numerical simulation, right? I mean, in the end I have to solve it numerically. So for this to make sense, certainly the answer has to be independent of the resolution that I use, right? So this means I have to adjust the variance of zeta. There's nothing else I can do. There's nothing else in the problem. Right? This will definitely happen. The only way to remove the n is if the variance of zeta square is made like n, right? And that will happen if the variance of zeta square has a 1 by delta t, because delta t is t by n. So this means that right, so for convergence I should not solve this. So let me keep this unit variance now. I didn't say this before, but let me say it with unit variance and 0 mean. Okay, so if I do this kind of zeta, I will not converge, right? So the only kind of equation that will converge when I have such fluctuating noise, right, where zeta is this random number, is if I account for a delta t factor. So, I mean, the funny thing is I can't even write this, right, because I cannot put delta t here, I can only put it here. Okay. So if you like, I should write a kind of difference equation. Okay, how did I get that? I said I want this thing's right now it has unit variance. I actually want its variance to be like 1 by delta t. Okay, but variance means zeta square, so zeta should go like 1 by root delta t. So I should get root delta t in the numerator. Okay, so that is equivalent. This is equivalent to saying, okay, let me leave it like this, but change zeta so that its variance is 1 by delta t. Okay. That's because I need this variance to go like n. Is that okay? So it's an important point. If you didn't understand, you ask me again. So now what I have realized is if I try to interpret it as an ODE, I am doomed. It will not make sense. Apart from the fact that this thing is fluctuating in some weird way and so on. So even just from this purely empirical way, if I try to simulate it, I am not getting anything meaningful. But if I think of it as a difference equation, that means I am not even saying I am trying to solve a ODE, I am directly thinking of only the computational exercise of random walk. Right, so forget about the ODE mathematics, I just want to somehow simulate a random walk which will converge, right, no matter the resolution at which I am looking at it. So if you like, this dt is the resolution at which you are observing the random walk and you are trying to replicate it at that resolution. So the physics I get from it should be independent of that, right? This x square should grow linearly in time in the same way, statistically speaking. Right? So when I say statistically speaking, the ensemble average has to be exactly the same function. So that can only happen if I solve a difference equation of this type. That means I say the steps dx is a random number of unit variance times a factor that depends on the resolution with which I am observing it. Yeah, 1 second. So this is crucial, right? So it's saying that to even construct a meaningful random walk, the forces I am giving have to somehow depend on the time intervals with which I am applying that force. Okay. But if you think about it from the physics perspective, right, of what these forces are, right? So I am looking at it at some time. Actually, in reality, it's being hit all the time at some very, very small scales that I cannot reach. I'm only choosing to realize a random walk at some intervals delta t, which are much larger compared to those microscopic hits. So if I start now, I wait for some delta t, it has actually had several hits. And this zeta is only a replacement for all those several hits. That's why I can say zeta is random. Right? Otherwise, if I'm actually resolving a molecular dynamics simulation, it won't be random, because there will be some configuration of molecules all around the particle, and at some arbitrary short time, they will be more or less in the same place, right? Because the molecules are moving smooth. It's only because I'm taking big steps compared to those molecular fluctuations that the instantaneous sum of forces now and at the next time ti are uncorrelated. But then the magnitude of that force should depend on the time interval, because I'm getting more hits, right? So if you think of it this way, that the random walk is a result of uncorrelated random hits, right? Then the longer I wait between steps, more hits are being accumulated, right? And they are random, so they'll keep adding up. Their variances will keep adding up. Right? That's what we did here, right? Right? So if I'm getting hits and each hit is uncorrelated, it's not that if I look at it at shorter intervals, the hits are the same. They're not. They're uncorrelated. So I could get the same high magnitude force and at the very next instant get the same hit again, right? Because that is my assumption about zeta. So if I wait longer to update, I should apply a stronger force, because only that accounts for the fact that I'm being hit with an uncorrelated random force. If I keep it same, it won't work. So that's what happened earlier. You see, I didn't have this factor, right? I didn't account for the fact that this step should grow with the delta t. So therefore, I was losing as n, right? Because they were weaker proportionally as I was making it smaller. But when I account for that thing, then it becomes independent of that time. So it's accounting for the fact that if I wait for longer, I should take a bigger step. Right? If I take more frequent steps, these should be smaller because I have less hits in some way. Right? But it's being done in such a way that no matter how small I go, there are infinitely more hits below that. That's because I said this zeta is uncorrelated. Now, why should it be root dt? We cannot say, I mean, of course, you can see this is a heuristic way of kind of doing it in the reverse fashion. But from first principles, a priori, I cannot justify the root dt right now. This thing ultimately will come, the understanding of why I need it to be like this, right, will come when I address the question I raised in the first class, which is how to understand a stochastic integral. In other words, I know I cannot make sense of this equation because if the zeta is some random number, then this ODE doesn't make sense, right? Because in a usual ODE theory, X will have a unique solution only if this zeta is Lipschitz continuous and so on. This is far from being that, right? It is fluctuating at every instant of time in an uncorrelated way. So this equation doesn't make sense. So to make mathematical progress, I'll have to write X as integral of zeta. And now understand what that stochastic integral is. And in the first class, remember I told you, because zeta is uncorrelated, that integral is not well defined. It will have different answers depending on where I sample the zeta. And if we begin with that and figure out the mathematics for stochastic integrals, we'll ultimately arrive here. Okay, so the correct way to get this is what we will do in forthcoming lectures. But already now, I just wanted to give you some feel, right, for how such problems are funny and why one gets this behavior. Just one second. So now, what is assignment 1? Assignment 1 is to essentially solve this equation. Okay, so now I have given you some basis for why you have this root dt. Okay, so we will treat zeta as a random number of zero mean unit variance. It can be Gaussian, it can be uniform, as long as the variance is kept same. And what you will do is then take a particle x and update it with these steps by tossing random numbers, and you see how the trajectory evolves. And let's see if you actually get this result which you derived theoretically. And you derive this result theoretically both using this equation following Langevin style. So I'm not worried about the kt, just the fact that it grows like t. So you could have replaced this mv square by some constant, doesn't matter, you will still get this result. Right? So you've just said the fact that on average the particle has some kinetic energy which is constant. So you can get this result this way, or you can say, okay, I know this is the microscopic process I am simulating. I can directly do Einstein's derivation, right? I say I have some steps dx, they have a distribution. The distribution is exactly the distribution you use for zeta. So if you take a Gaussian distribution for zeta, then phi is Gaussian. The phi of delta, remember, this is delta. Right? So the phi of delta that Einstein assumed is just Gaussian, it's just this distribution. If you take uniform, then it's a uniform distribution. In either case, you will get the basic things, which is the mean of phi will be 0, and the variance of phi will be the variance of this, right, into this root, into dt. Okay. So if you simulate this as your reality, right, which you are trying to model, either Einstein's derivation or Langevin's derivation will work. So by doing the simulations, you should get that the mean square displacement x square should grow on average linearly in time. So that's what you will check in the assignment. And then you can check other nice things like verify that this answer that you get is independent of the resolution. Okay. and also that it doesn't matter what distribution you use for zeta, which might seem surprising, right? That I can take Gaussian, where in principle zeta can go to infinity, right? So Gaussian doesn't have any limit, right? It falls off, but there is always some finite probability to take a large zeta, whereas uniform will cut off. There is zero probability beyond some level. So one might think these things should do different things, right? But you will see the level of x mean square displacement, they should give exactly the same answer. But we already know to expect that from Einstein's derivation, because that's what we saw. So this means the Gaussian falls away fast enough. But there could be other things which has some variance, which have fat tails, then it may not work. Okay, so this will give us some feel for things. That is assignment 1, it's already on Moodle. Yeah, there were some questions? Yeah, so the reason this comes fundamentally is, as I said, it comes from understanding the stochastic integral. Okay. No, it's not. Right, so you would have to do this regardless of what property I want to investigate. Right? Even to get converged trajectories, I would have to do this. So what I mean by is, imagine you have, you sample the random number at finer levels, but in such a way that at the coarse delta t you have the same numbers. Right? Then you can imagine somehow the trajectory converging, right, in some statistical way. And for all those things, no matter what property you look at, this is the way to do it. Right? So this doesn't come from, it's not that because I'm looking for mean square, this works out. I just use the mean square to show it, because it happens to show it here. But it's a fundamental thing that comes from the stochastic integral. So when I define the stochastic integral, define it mathematically, it makes sense of it rigorously, then there will be an obvious discretization, which will be this. Okay, and that's only for this so-called Ito calculus. But we'll have to wait to be fully comfortable with the root dt. Exactly, so that is just, let's go ahead for now. So these are exactly the problems that were actually there, right? People don't know what to do. So it's like when Newton introduced the calculus, that there were infinitesimals hanging all over the place, people don't know what was going on, right? And somehow you could get the right answer if you did the right stuff. And then it took maybe some 100 years plus for people to develop epsilon, delta, notion of limits, etc., and do everything rigorously. So still today in school we use these infinitesimals to derive derivatives as a shorthand, but we know that really what is happening we can prove. So this was some similar situation kind of re-encountered here, right? That you could do something, you could get an answer, but you can't justify each step, and if someone didn't do exactly the right step at the right time, you would get stuck. So all that was going on, because exactly what you're saying is totally true, I should not be able to do this. Right? So right now this is all just hand wavy, and it did take time to figure out how to do this properly. So we will do that from the next class onwards. So how does one systematically, so in fact in the end it will be that you cannot write this. Right? Such an equation doesn't make any sense. It only makes sense to think of difference equations. And this also will really come out of a stochastic integral. So the ultimate answer to the question, if I go ahead, is to say if I want to define a stochastic evolution, I cannot write an ODE. I should not even, strictly speaking, write the difference equation. I should only write the integral equation. So I say that there is a variable x which is evolving stochastically, and its equation is x is equal to integral 0 to t something, okay, which is a stochastic integral. But then I can reinterpret that as steps in x, which is difference of integrals, and then with that understanding, I can define this. But the meaning of this also has to do, mathematically speaking, only with the stochastic integrals. Okay, so that's what we'll do. We'll see how that works out in the course. So ultimately, one can, what makes sense is only difference equations, okay, then SDs. You will find in many, especially physics books, that something like an ODE is written, okay, but that doesn't make sense. Only this makes sense. So if you see anything like this, you have to interpret that this thing has a variance of 1 by dt, or a typical magnitude of 1 by root dt. And then when you discretize, you will get this. So that is somehow implicit in textbooks. When you see this, they will say, okay, this zeta represents the Wiener process or something, and they'll go on with it. Right? But the proper way of writing it is only this. And they will not even write, so that we will come to. Okay. Any other questions? But the message is, you should not think this is okay, okay? This is not okay. This is just a way for us to feel our way into the subject. Whatever you want. Yes, so the details about, so the questions about the assignment, the details of the assignment are uploaded. You can take a look at that. Okay, so thanks everyone.